This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. Somebody forgot to charge the mobile microphone, so I hope these desk ones are recording well. So I would like to start with a couple of announcements. Maybe the most important one is the mid-semester test is in 2 weeks, as you know, right? So I've started also preparing it. You should also prepare for it. And it will cover the optimization topics. So I think that will be the all. Next week we will start with machine learning, but I don't think I will have questions from that. I might, sneak in machine learning questions, but they will be in the form of optimization, so that's kind of doesn't matter. It will be optimization questions. So what else? I also posted some, more material for those who wish to, improve their math skills. And now in LMS resources, there are a lot of good links. Have a look at it if you need. And finally, I'm really happy with the lot of questions I'm getting during the lectures and afterwards. I much prefer the face-to-face ones. I try to answer emails, but if there are 180 people, if you start to email me continuously, I will be doing just email answering. So I very much prefer you to come to the consultation hours or ask your questions face-to-face. Until now, I've been managing it actually with the emails as well. But so that allowed me to make an update in the slides, and you can find updated slides in the lecture, notes. And when you prepare for the exam, make sure that you go there and download the latest versions. Don't study with the old versions. So I kind of, especially I spent the time putting this notation from Leuenberger's book, which is can be a bit mysterious. I tried to, demystify it by writing the vectors and matrices in a more explicit form. So you can see it here, the tangent plane general format for multiple equality constraints. And then, in this page, the first order necessary condition, and then what does this mean, and the Lagrangian for multiple, again, equality constraints for the equality case. I also changed the figure for the box, because the other figure was wrong. So I found another nice box figure. So our box is proper now. And then what else? The second order conditions. I have also put some nice stuff on bordered Hessian, which wasn't difficult because it was in the Wikipedia article. So I shamelessly copied it from there. That's good. So we did question 4. We didn't do question 5. And then we started with inequality constraints. And I have a new slide on the active-inactive constraints as well. But maybe before that, this is new stuff for you. And it's best we do practice a little bit more. And I think the question 5 that we skipped last time to start the discussion on inequality constraint, we can now come back and do it. So, that will give you an idea what is going on once we solve it with this Lagrangian multipliers and Lagrangians. Let me see. So I hope you can see it, right? So we can make it a bit bigger. So this is about the Markov chains. So it says consider a Markov chain with n states and a transition probability matrix, right? So we have, remember Markov chains? From probability subject? Right, so you have a Markov chain, and then you have the transition probabilities between these things, and that is represented by this transition probability matrix that you see here, given as, it's a bit written in a different way. The columns add up to 1 because the probability of the next step, yt plus 1 being node I, given the previous one is j, is pij. So kind of they are given in that sense. So the columns add up to 1. So Pij, so it will be then let me write it this way. Because it can be written in both ways, right? Rows can add up to 1 or columns can add up to 1. Which one represents what? For example, if this is I, and then all the transitions from I to the neighbors, then will be in the column. So Pij in this case is, no, you see this is the difference. So the previous one is J. So the jth one, and then from jth one, you go to the others, to the other I's. So that's why you have it written as, for example, P11, P21, Pn1. It's an n by n. And you have the jth node P1j, j to 1, probability of j to 2, but it's written as the P2j, and Pnj, which means probability from jth node to the nth node. So all those probabilities add up to 1, so the column j adds up to 1. And that's what it says here, actually. All of the probabilities are non-negative, of course, they're being probabilities. And then there's transition probabilities, starting from a node, they need to add up to 1. So the problem, is this clear now? Refresh a little bit the memory. Right? You can do that later as well. So this is the mathematical definition. And then, the problem is interesting. Estimate the transition probabilities given an observed sequence. This is very real life, really nice. So we have a sequence of observations. At time 1, we are at state K1. At time 2, we are at state K2. And with time n, we are at state Kn. And these Ki, the Ks are belonging to the set of nodes. So those are one of the nodes. So the system jumps from node to node, and I make n observations. All right? So the question asks, show that if there are no other prior constraints on Pij, then the maximum likelihood estimates are the empirical transition frequencies, and that is the ratio of the number of times the state transitioned from J to I divided by the number of times it was in J in the observed sample. So essentially it just says count the number of transitions divided by the times it was in the node J, and count the number of transitions from J, and do this for all the nodes. That will give you the best estimate, maximum likelihood estimate. I haven't covered maximum likelihood, but the name is a very good name. It says what's the maximum, likelihood of something. What is the kind of maximizing that probability of something is true, right? Is that maximizing the probability of the observed sequence given the transition probabilities. So what we are trying to do is find the transition probabilities, find this matrix Pij, such that we maximize the probability of the observed sequence. So actually, you can also think it the reverse way. Given that sequence, what should be the transition probabilities so that my observation is the most likely observation? Does that make sense intuitively? So if I find the right model, that right model will most likely of that right model, or the most the sequence that we have observed will be the most likely sequence. So maybe writing it mathematically might help. So what have we observed? We have these transition probabilities from K2 to K1, probability from the first node to the second node, from multiplied by the probability that second node to the third node, because it's J to I, and then if I multiply these probabilities of the sequence, the sequence is observed is Y1 is in K1, Y2 is K2. So therefore, the probability of going from K2 to K1 is PK2, K1, right? And then the next one is, then I go from K2 to K3, not K3, whichever node that is. So that means that is the probability of going from that, K4 to K3, and then K3 to K4. And if I multiply all these probabilities with the last one, Kn, going from Kn minus 1 to Kn, Yeah, actually this should be capital N, but let's skip that. So all these probabilities multiplied, will be the probability of the sequence that we have observed. So that's the probability of the sequence, and I can write it as pi ik equals 1 to n, and then I can write it as pij. Of course, you may go from one node to another node multiple times, so those probabilities appear multiple times. So I put an exponent Cij, where Cij is number of, let me write it with this, number of times I, number of times state transitioned from node J to node I. So this probability, then that is the probability of the sequence, right? This is the probability of the sequence of that specific sequence. I find the probability of that sequence. Because it's a specific ordered sequence, I need to multiply the probabilities. What is the probability of going from 1 to 2 times 2 to 3 times 2 to, all the probabilities are not ordered, added up, they are multiplied. Because it's an ordered sequence that I've observed. So this is the maybe explain it in a sentence verbally. This is the probability of the observed sequence y1 equals k1 to y2 equals k, node 2 equals, at the state y being in k1, state at time 2 equals k2, ... state at time n is kn. Actually capital N. This could be a longer one because there could be multiple cases. You may come back to the same state node multiple times. Therefore, we have the Cij. Those probabilities appear again and again. Therefore, we write them to the exponent, right? It's a number there. So this is the probability of the sequence in terms of transition probabilities. Probs of the Markov chain, which is Pij, right? If I'm giving the probability, transition probabilities, what's the probability that this sequence happens is this. Okay, that you should be able to, convince yourself if necessary later. So, what is the maximum likelihood? If this is the likelihood, then I just maximize this. As the name indicates, if this is the likelihood of the sequence of my observation, all I need to do is maximize this sequence. So, I can actually, what am I trying to find? Again, let's do it again as we did before. Decision variables. So that's always useful. What is our decision variable? Variables. You tell me. We want to find the model such that this observation is the maximum, most likely observation. So observation is already done. Counts are counted. Cij is not in my hand. But these probable, and then the sequence of nodes is what I observed. The state y is n over an n horizon, capital N horizon. It wandered through the nodes. Well, I don't know the probabilities, right? I don't have the transition probabilities. So that's the model that I need to determine. So the model is decision variables are Pij for all for all ij, or I equals 1 to n, and j equals 1 to n, right? Okay, those are my decision variables. Clear? So I'm trying to identify the Markov chain that is so that observation is the most likely observation coming from that Markov sequence. So I need to maximize then this likelihood. So maximize So all I need to do is maximize Pij with the likelihood Pij to Cij, over the multiplication. But this is actually cumbersome looking. There is a well-known fact that's also in Boyd's book that we can use to make this easier. So use the trick. So the trick is this. So I don't think I've mentioned this before. This is very often used, and we will come to this again and again. Actually, maximizing of a log of a function, because it's a monotonic transformation. Maximizing the log of a function is the same as maximizing f of x. Of course, the number itself will be different, but x star will be the same. Why is that? When you maximize log of f of x, just as a quick justification, when you take the first order condition, you have f prime of x over f of x, right, equals to 0, and then the first derivative equal to 0, but that's the same as the having this equal to 0, you see? So, and the same for the second derivatives as well. So, that's the trick. Why does it help here? Because that multiplication becomes addition. When I take the log of, pi, Pij, Cij, that becomes, log of multiplication becomes addition, Cij comes into the front. So I end up with actually Cij log Pij. Right? And that's nicer. So addition of log terms. That makes life easier. Okay, so that's the decision variables was that. Objective function is the likelihood. So I'm maximizing the likelihood, which is equivalent to maximizing the log likelihood, which is always done, also in machine learning, repeatedly done, due to maximum likelihood being used. So that probability, I maximize the log of probability. All I need to is then write it down as a is an optimization problem, right? What was the question asking me? So show that first we need to write it to solve it. So let's write it down. So we have to max. So therefore the problem is max Pij sum over Ij Cij log Pij. That was Ik. You can make the Kj. So this is the same thing. And then subject to, do I have constraints? Yes. Remember the columns need to add up to 1. The matrix, transition probability matrix should have probability vectors as the columns. So therefore it is subject to, we can write it again simpler as J. No, that would be I, right? Sum over I, Pij equals 1. So those will be the rows. I's will be the rows. So essentially we are saying this should be, add up to 1, right? And all of them have to add up to 1. They're also positive, but I'm kind of skipping that to simplify my life. Also, we have the Pij greater than equal to 0. The probabilities cannot be negative, but I'm kind of skipping for now because this will not play a role. To make a bit simpler. So, and this has to hold for all I, right? For I equals 1 to n. So actually I have n constraints. N columns, n constraints. So from Lagrange multiplier theory, what we know is n constraints means n lambdas. For each constraint function, you should have a lambda. Right? 1 lambda per constraint function. Lambda I per constraint, right? Constraint I, right? So I will have a lambda vector of lambda 1 to lambda n, right? And just follow with me because we are doing it for the first time, right? You haven't done this before. So what we do next is, now that I have the problem, I need to write the Lagrangian. So that is a nonlinear problem, but linear equality constraints. I can write my Lagrangian function, which is f of x plus lambda transpose h of x if h is a vector. But the good thing about this is actually this problem is decomposable. You see, each of the constraint is only applying to I, and then this maximizing Pij, there is this double sum over I and j, right? So for each I have a sum over j. So actually I can write this as, separate the problem first before I write the Lagrangian. We can separately solve the problem for each I, which is the column. Right? That makes, if I can pull this trick, it's really good. It also simplifies the problem. So we can solve it one by one. Then the Lagrangian will be, of course, simpler. So if I write this down, they don't affect each other. Usually they affect each other, right? Here everything separates nicely and doesn't affect each other. So once I do that, so I have done this. Did I say I? I should have said j, right? I'm sorry about that. Did I say I or did I say j? But actually I should have said j, because columns are j. Because their columns are j, right? This is j equals j, j equals 1, j equals 2. I's change. I's are the first numbers. So actually, yeah, I should do this like this. So I have the j. The sums can change places, right? That's not a problem. So we have the j and I. And then you have it for each j. 1 lambda j per constraint j. That's the other one. It depends on how you define the Markov chain. You could have done the transpose of the Markov chain. It's just a matter of definition and being careful with the definition. Okay, so for each column j. So now I can write it for each column j, the problem. The problem per node j or column j is I sum up over I, Cij log Pij subject to sum over I, Pij equals 1. Okay, now this is clean. I can write the Lagrangian, which is f of x plus lambda. There is only one constraint here, right? So it will be a scalar lambda, f of x plus lambda times, constraint, which is the sum Pij minus 1. That is a scalar because there's only one per problem. So in this case, then Lagrangian will be sum over Cij, which is over I, log Pij plus lambda, again I, Pij minus 1, right? This is the canonical form, Pij minus 1 equals 0 form. Good. So once I have the Lagrangian, now I need to solve this for x and, lambda. And x is the pi's. So I have a vector Pij to solve for the jth one. So this is like Lj. All right, let me put that. So, not to confuse things. So I write the, what do I write? I need to tell del with respect to P, Pij equals 0, and then with respect to lambda equals 0. But when you take the derivative with respect to lambda, that's nothing but the constraint itself. So that we already know this. That is the constraint itself. Right? When you take the derivative with respect to lambda, this goes away, and the constraint equals 0, but that was the constraint itself. So we already know that. When we take the derivative with respect to Pij, what do I end up with? With respect to the ith Pij, then because it's over I, only the ith one remains, so I end up with Cij divided by Pij, and then Pij, all of the i's are here, but if I take the ith one, then only one of them is there, multiplied by lambda, that goes to 1, so lambda is plus lambda, right? So that is equal to 0. And I get then lambda star, the solution is actually as a function of actually lambda from here. So now I need to solve for lambda. Lambda equals minus Cij over Pij. If I substitute it back now to the substitute, and then therefore I have this, that means Pij equals minus Cij over lambda, right? They are that. So if I substitute this into the constraint, so then that will be sum of Pij, which is minus Cij over lambda summed equals 1, right? And then lambda will be then actually this whole thing can be made a bit simpler by putting a minus sign in front, because this is an equality constraint. Lambda is any real number, right? So this minus sign, then we can put it there. If it is the wrong sign, then lambda will be minus. But by putting this sign, you will see that lambda will become plus. I don't have to write all minus signs everywhere. So this makes it a plus. So then lambda equals actually 1 over sum over Cij. So this is actually my solution. This is the lambda. Then, in order to find Pij, now I need to substitute it back to get my solution. Right? Therefore, Pij is Cij divided by sum over Cij over I, right? So this is the over I, because this constraint is over I. So this is the actually counting how many times I went from j to I over total number of times I have exited from that node. But that's kind of intuitive result when you try to estimate those transition probabilities. How many times has I moved away from the jth node to other nodes, and then jth node to the ith node divided by that total gives you a kind of an estimate. It is then the maximum likelihood estimate of that probability, transition probability, that will give me. So this is the maximum likelihood estimate of Pij for maximizing. What does it do? Maximizing the likelihood probability of the observed sequence. I will come to this maximum likelihood, but if you get confused about the whole maximum likelihood thing, you don't have to understand it perfectly, but this is just an example of an optimization problem, right? I have taken that estimation process, turned into an optimization problem. From that point onwards, it's an exercise in doing a little bit of solving a specific linearly constrained convex optimization problem. Because I'm maximizing a log, therefore it's maximizing a concave function. That's same as minimizing a minus log, which is convex. So it's a convex optimization problem because of the constraints also being linear. All right. So this is so what if I know more? There's another nice thing about this question. So let's say you do this, and then the question says, but what if you know that there is actually the stationary distribution, right, of the of this Markov chain, and I know that stationary distribution, which is Q, right? The equilibrium distribution of the Markov chain is known. So if you don't know optimization, you will scratch your head. How am I going to embed this to the problem? How am I going to find these PIJs again? But because we have done the hard work and posed it as an optimization problem, now actually putting that additional information into the picture is trivial. So the whole thing becomes, what was it originally? The whole problem, this one. This was the original problem. And then just add PQ equals Q, which is the stationary distribution of a Markov chain, into the constraints. And done. Right? So we just have to put it back in. So then we have the max Pij double sum Cij log Pij, and then the columns should be added up to 1, and P times Q equals Q. Yeah, and that's it. So now you need to solve this, of course. Now we will have another set of lambda tildes, equality lambdas for each of them. So you will have now here n constraints, another n constraints. So lambda will be then size of 2n, right? Or you can put lambda 1 to n for that, and then lambda tilde 1 to lambda tilde n. So you have a longer vector, one Lagrange multiplier for each equality constraint. And then you need to solve it in a similar way. But it will, of course, change the answer, but you can also do it numerically, right, with the software packages. So I'm not going to do that one. Just tell the questions also are not asking you to solve. I may actually in the exam just say, give the problem. That's a legitimate question. Just, pose the problem. So this is the answer. So this is the answer. So you don't have to solve it by hand. Let the computer solve it for you. As long as you formulate it correctly, you're done. So that can be an intermediate or actual quite practically a stopping point. Any questions? So again, even if you don't remember the Markov chains, it's just a linear, just a convex optimization problem with linear equality constraints. And how you do the Lagrangians, how you find the lambda by hand. Okay, this is a kind of because it's simple, you sit down and solve for a single lambda. Because it decomposes, it's a simpler problem with a single lambda and n Pijs for a given j, so that column vector. And then because of the simplicity of the structure and log and so on, you can solve it by hand. Of course, not every problem can be solved simple like this by hand. Then you need to give it to the computer to do its job. All right. So, wow, time flies. Oh no, this doesn't end off good. I was really shocked. Let's continue with the new slides, the inequality constraints. The difference between inequality and constraints and equality constraints is equality constraints are always active. You need to honor them, and they need to hold, right? You cannot say, I'm going to disregard that equality constraint. It always has to be valid. But inequality constraints, if the g1x is less than 0 for some x, that constraint you can as well say, for that x, this constraint doesn't play a role. There could be some points for which those constraints are not active. So therefore, we can talk about a set of active inequality constraints at a feasible point, at any point, not only at the solution. Of course, the solution point is the most important one, but at any point x, we can have this set AX for which J, let's say we have R constraints, R inequality constraints, indeed G1 to GR in the standard format, and then such that Gjx is equal to 0, that means this constraint is active. So that's the active set. how about those others for which Kx is less than 0, strictly less than 0? That means at point x, those constraints are as if they are not there, because they don't play a role, right? So if the constraint is not inactive, we say that constraint is inactive. Now I have added this new slide to hopefully make things a bit more, more clear, active and inactive inequality constraints. And we are looking at the optimal point here, x star. But this is, active set can be defined for any point, active and inactive set. So for x star, you see, if x, this is the level sets, right? And let's say we are minimizing, so this is the bottom of the valley, for example. Or it's the top of the mountain, doesn't matter actually. So you see, this is the constraint. Gix is 0, and inside Gix is less than 0, right? So this is my constraint set, as defined by that specific constraint. Of course, I will have many of them, and then I need to take the intersection. But let's say this is the only one. You see, I get the solution, and this doesn't play any role. It doesn't change the solution. But this is still the bottom of the valley. But what if I slightly shift this and create an Hix, different constraint? You see, now this is outside that constraint set. I cannot find the unconstrained solution. Now the constraint dictates what the solution is. But constraint dictating solution means it has to be on the boundary, if it's a convex set. Yeah. Even if it's not convex, that's the same, I guess. We don't have to even say that. So then the boundary is dictating the conditions. So at that point, in this case, right case, this has turned into an equality constraint, and it is active, right? Otherwise, the constraint will not be active. Wouldn't play a role. So that's the sentence here that you should kind of carefully read, and let me know if I had put the typo. I tried to write it carefully, right? So then for a general problem, this is the canonical form of an optimization problem for continuous case and also convex optimization. Let's say I try to minimize an objective subject to some set of when it's written like bold like this, it's a vector kind of like a set of equality constraints, and then there are a bunch of inequality constraints, G1 to GR, maybe H1 to HM, I don't know, they can be different numbered, and less than or equal to 0. Then when I write the Lagrangian and take the derivative as the first order condition, and if I write also the complementary slackness condition, I'll come to this, then these are called the very famous Karush-Kuhn-Tucker conditions, KKT conditions, right? So KKT conditions are the counterpart of the first order conditions when you have unconstrained optimization. And this is the most general because it takes into account linear constraints and equality constraints and inequality constraints. For equality constraints, lambda can be anything, any real number, lambdas, elements of the lambda vector. If it's multiple, it is a vector, of course. 1 per each. And then mu, that's here, we call them now the inequalities, we associated them with mu1 to mu r, let's say. If it's a minimize and you write it this way, then mu's have to be positive. There's a reason for that, but it's a longer story, but just take it on the faith. So the Lagrange multipliers are always non-negative, mu greater than or equal to 0. So these red lines are kind of repeating what the previous slide said. If the Lagrange multiplier of a constraint is positive, then that constraint is active. And if the Lagrange multiplier of a constraint is 0, then that constraint is inactive. Actually, these two together describe this complementary slackness condition. So if this is active, then g of x star has to be 0. And then mu is greater than or equal to 0. And if it's inactive, then g of x star is not 0, maybe less than 0. But then in that case, mu is 0. So then the multiplication is again 0. So the multiplication is always 0. So this is the famous complementary slackness condition of the as part of the KKT. Right, so that takes into account the activeness and inactiveness in addition to this first order of the Lagrangian. Okay. Now, there is something that's worth mentioning, and then we will do it with this question. So, we have to, I think I've put too many questions. I will have to give you some of them as, as homework questions or something to study at home. I mean, not homework, but because I'll give you the answers. It's not a problem. Otherwise, we will never come to machine learning. This is what I'm starting to fear. This is we are in a bit rabbit hole. I was overly enthusiastic. It is good to have. I thought it's good to have many questions. I can skip them, and yeah, it is necessary to skip some of them because some of them are repetitive exercise, which is good. Good to have, but yeah. There's one thing that I mentioned in the beginning, and you may have forgotten. This regularity business. A point satisfying the constraint is said to be regular point of the constraint if the gradient vectors of the constraint are linearly independent. Right? But what if they are not linearly independent? What do you do then? It turns out, if this regularity doesn't hold, you don't have Lagrange multipliers. And that's a bit strange, and it's important to kind of know this. Otherwise, you will think, oh, there's always a Lagrange multiplier, but there are sometimes no Lagrange multipliers. And question 6 is a good illustration of the case. Again, this is a simple thing so that, simple question so that we can solve it by hand. So it's kind of one of those questions where we already know the answer, before solving it. All right, so the question is this. What is QCQP? Let's play riddles. Q is quadratic, C is constraint. So actually this is quadratically constrained quadratic program. Yeah, but that's a very good name. If you think about it, what is the objective function? It's quadratic. How are the constraints? They are quadratic. So it is quadratically constrained quadratic program. Right? You see the constraints are quadratic, right? And the objective is quadratic. So if the objective is linear and everything is linear, it's linear program. If the objective is quadratic and the constraints are linear, then that's quadratic program. If the objective is quadratic and constraints are quadratic, then it's QCQP. My favorite is what you see is what you get. Then when you write that as a shorthand. Anyway, let's get back to the program. So actually the question says sketch the feasible set and blah blah blah. Find the optimal point and optimal value. Actually, I've kind of put it there. So if you know these are actually circles, and then not the circles. The whole area, right? Is because they are inequalities. So we have these two perfect disks, and then they are located in different points. This is the center of them, right? Their radius is 1, right? So both of them are constraints, so you need to look at the intersection set of the constraints. And then minimizing x1 square and x2 square means, if you can, you should go to 0, right? Or as close to 0 as possible. But reality is, what is our what is our constraint set? Can you visually see what is the constraint set? So one of them is one constraint, the other one is this other constraint. What do you do these constraints? You need to satisfy both of them at the same time. You do AND, right? AND means what? Intersection, right? So what's the intersection? Actually, this is the intersection. There is a single point. Right? This is a very nice special. I told you, if they don't intersect, you have an empty set. Empty set means the problem doesn't have a solution. Here the problem has a solution, but there's only one option, that intersection. So you don't need to worry too much about what the objective function is. So actually the solution is, if you look at it, the only feasible point is point is 1, 0, x1, x2, x1, x2. So this is, when you plug it 1, 0, you will see it satisfies both constraints. Yeah, if I put 1, 0, what is it? Then 1 square less than equal to 1, and then 1, 0, it is, first one goes away, 0, then 1 square less than equal to 1, check, right? There is no other point doing that. So the only point is this. Therefore, solution is, x1, x2 is 1, 0. That's my solution. And then x1 square plus x2 square, the value will be then 1, right? Fx star will be 1. Good. So that's the value of the optimization problem. That's the argument is x star. So this is, I think this is the star, right? Okay. So now, but let's do it the long way. This is obvious, but let's do this as an exercise to the KKTs. So let's quickly write the Lagrangian. That's why it's good to have something so we can understand what's going on. So I have 2 constraints, so I should have 2 Lagrange multipliers. And because it's a minimize and then 2 inequality, so I write lambda, but in the canonical format it's mu1, mu2. I could have written as mu1, mu2, but let's write it this way. So I can write then x1 minus 1 square plus x2 minus 1 square minus 1 less than equal to 0 plus lambda 2 x1 minus 1 square plus x2 plus 1 square minus 1 less than equal to 0. So I multiply that. So that's my Lagrangian, right? So now we can write the KKT conditions. So we have the KKT conditions. We have the del L. So we have done del L to del X, del L to del Y, and complementary slackness, lambda times constraint equals 0, right? So if we write these down, so we get then the original constraints. X1 minus 1 square plus x2 plus 1 square is equal to 1. Then I have because they are inequality constraints, the Lagrangians can, and then I have carefully written as plus lambda for a minimization problem. So you need to be careful. Minimization problem, inequality constraint in canonical form, plus lambda means then the lambdas have to be greater than equal to 0. And then I take the derivative of this L with respect to Lagrangian with respect to x1 and x2. Then that gives me, if I take with respect to x1, it would be 2x1 plus 2 lambda 1, x1 minus 1 plus 2 lambda 2, x1 minus 1 equals 0. And then equate to 0, right? So these are all equating to 0. And then if I take with respect to the x2, then some terms cancel. Lambda 2 x2 plus 1 equals 0. And complementary slackness, this is important. So I should lambda 1 times the first constraint, g1x equals 0, and lambda 2 times g2x equals 0. Now, at x equals 1, 0 at the solution, right? KKT set KKT equations. It's a set of equations, right? All these. Let's make them nicely green. All this crowd, right? The set of equations. They have no solution. I will post the full. KKT equations have no solution. If they have no solution, there is no lambda. But there is a solution to the optimization problem, right? They have no solution. There is no lambda. There is no Lagrange multiplier, but there is a solution to the problem, because we destroyed we kind of we contradicted the regularity requirement. So because we violated the regularity requirement. Because we violated regularity condition. Because the theorem says, you know, Lagrange multipliers exist only if regularity is satisfied, which is the gradients of the active constraints should be linearly independent. But what are the gradients of the active constraints? Actually, gradient of G1 is 0, 2 here when you, at x star. And gradient of G2 at x star is 0, minus 2. You see, they are linearly dependent. One of them is just minus of the other. They are not independent. So therefore, they are linearly dependent, which is not something we want. We want them to be independent. Therefore, we violated the regularity condition. Therefore, there is no Lagrange multiplier. And this is a really nice example because it's an obvious example. You see, there is a solution, but the Lagrange theory doesn't apply anymore because you violated the regularity conditions. So, you know, we should be, you know, this is not something that the computer will warn you, right? If you give the computer a problem with this, actually, I asked it as a bonus question. I don't know what the solvers do. In the workshop, remember, there is a last bonus question without any points. So kind of, I don't know how computer packages will handle it, but most of the computers are not terribly clever. So either they will throw an error saying they are linearly not dependent, or I don't know what they will do. All right. Last word of the day is, yeah, I need to give some questions of the set as the home study. Then that means I will give you the solutions, and then we will maybe discuss them over the consultation hours and so on. And then the other thing to say is, but I'll still need to do some duality examples, so I will continue that next week. Other thing to say is, this is an example of constraint satisfaction. There's a whole field called constraint satisfaction problems. So if you have a problem where you have so many constraints and finding a feasible set is the challenge, then that is the, you know, this is the class of constraint satisfaction problems. For those people who work in that field, objective function doesn't matter too much because you have so many constraints. They only try to find one feasible solution, one non-empty set out of the given constraints, and the constraints are very, very intricate and complicated. So this is a nice example of that. If you make them too intricate, you end up with one solution, two solution only. The objective problem doesn't play a role anymore. You are just trying to satisfy the constraints of the problem in a difficult, optimization, over the constraint optimization situation. This is not over the constraint. There is a single, at least it's not an empty set. So the problem is a proper solution. But there is no Lagrange multipliers, and that ends it today. So, and then I will continue next week, maybe the first lecture with optimization, tie it up, and then start with the machine learning. So it is possible that you will do a little bit of machine learning workshop before we go to the material, but I'm perfectly fine with that. It will make you curious about the theory. And the slides are there anyway.